Excellent. So thank you, Michael, for inviting me today. It's wonderful to be here, and greetings from very sunny Athens. I left Berlin a week ago, and I must say the weather is a bit better here. So I'm Suresh. I'm the VP of Data at Beat, joined recently. Beat is a ride-hailing similar to Uber or FreeNow, and actually Beat is actually owned by FreeNow. So even though I've left Germany, I can't escape Germany as it's my big boss. So today I wanted to talk about complexity, simulation, adaptation as much as I can in 10 minutes. It's very heavy topics, but I was happy to see some philosophical talks before as well. My background is in theoretical physics, and actually this takes me some topics I did research long ago. So as I said, Beat is a ride-hailing app with multiple services, including actually in Mexico City, a Tesla service where we actually employ the drivers and own the vehicle, so very different. But as you know, urban mobility and ride hailing specifically is a marketplace, right? So it's a marketplace matching passengers to drivers. We charge the passengers a fee, a price, and then we give the drivers a commission. And that's how the economics of the whole system works. So let's start off with some data science, some topics that people already mentioned. I'm going to go through this fast so we can get to the meaty topic later. But obviously in ride hailing, there are a lot of things you can do in data science. Typical things, obviously, like forecasting, if we start with some advanced analytics, so understanding trends. Obviously, trying to forecast demand is very important, and making sure that the supply can match. Segmentations are very important, frequency and behavioral, understand the evolution of customers as we do in all businesses, especially e-commerce and marketplaces, targeting incentives using CRM. Ride hailing is very much driven by incentives on both sides of the marketplace, actually, especially more so for the drivers. And of course, understanding experimentation. We're very much an experimentation driven company, and you use the segments for that. Going to the next level up to machine learning, I'll call it machine learning. As somebody mentioned previously, terminology evolves and changes. It's basically marketing. So here it's about predictive modeling in the end. That's what machine learning is about. And also about some ranking and recommendation. So on the predictive modeling side, churn prediction, very important, as was said previously, has been going for decades. Great value from that. Understanding how drivers respond to incentives, also called uplift modeling. And then on the passenger side, understanding how sensitive to price are they? You know, can we increase the price more? Can we be charging more and making more revenue? Then on the pure product side, as I said before, we have multiple services. When the passenger opens an app, can we rank it so that they have their service ready, pick and go? Can you go even further and predict where their destination is? This is something we're thinking about, and others are as well. You can go beyond that to actually, you know, we think about data science typically about prediction, CRM, and so on, but you can also use data and data science for business models, evolving the business models, which is very important in urban mobility, as is a very young industry. You can have personalized pricing for the passenger side. You can have personalized commissions for the driver side. And you can also think about new ways of charging. Can we have subscriptions for the passengers? Can we have a driver loyalty program, right? A commission ladder. The more they drive, the more rides they have, the more the commissions they earn, and so on, all to encourage engagement and loyalty. But something that's interesting about urban mobility, and this is the main topic, is actually we also think about system optimization. I think most people who've used Uber, FreeNow, or so on understand surge pricing. You know, in high demand times, especially weekends. In the old days before COVID, if you're trying to get to a party in Berlin or a club, then the price is higher, right? Because there's huge demand. But it's not to just gouge money off the passenger. That's not the reason for surge pricing. It's actually to get more cars on the road to meet that demand. So it's to motivate the drivers by saying, hey, we're going to pay you more in the end due to the higher price. But of course, there is the secondary effect of the incremental revenue. So you need to balance this driver with the passenger side. And that's system optimization. That's really what I talk about. And you don't think about system optimization for e-commerce, where it's really a relationship one-on-one. So let's talk about that. So ride hailing actually involves a lot of complexity. Because of this, there's lots of cars and drivers and passengers. And actually, when you think about it, ride hailing is just not a simple digital system. It's an ecosystem, right? There's our ecosystem within Beat of the different types of customers, the different types of drivers, the different types of services, but then there's competitors, Uber, Didi, different types of customers not with us. There's public transport. So it's an ecosystem, and actually it's very complex. And what does complex mean? And this is this very scientific term. To give you an example of thinking about systems, thinking, and complexity, let's go back to a simple frequency distribution. One of the most simple things you can do, and you might say it's not even valid to be called advanced, but it's actually very powerful. So here's a segmentation showing for one of our markets in Latin America, going from high to low frequency. And you can see typically you have this Pareto distribution where there's a small number of high frequency drivers, but they have a greater share of the rides, right? So this is typical in most businesses, definitely in marketplaces. And then the Pareto ratio at the bottom is the ratio of rides to drivers. So our super high frequency have a higher ratio than our low frequencies, which are barely giving the output, right? Now, if I think about this, and I think what's important about these segments, and actually something we're working on is optimizing these segment ratios, right? When you think about ride hailing and you think about the drivers, we need enough drivers there to make the system run, right? So we need stability. So it needs to be stable to slow changes. Are there enough cars that can come on when there's a slight increase in traffic or as we grow the system? We can also think about resilience. We heard the word resilience before in terms of systems, and resilience always refers to systems, the dynamic shocks. What if there's a massive demand today? Can we adapt to that, right? So that means, do we have enough drivers in our system, even if they're not on the road today, to bring on to react, right? And you can think about this as a system level thinking. Should we in fact take a loss on low frequency segments, right? So give them incentives so that they're always there and bring them online to react to these dynamic shocks, right? So we make money by losing on one small segment, but optimizing the overall system to make money. So that's what we think about system level optimization. And it's very different than just interacting with the customer one-on-one. Surge pricing, as I said before, surge pricing, I mentioned it just as system optimization, but when you look at it, it's not just getting more drivers. I just showed you the driver segmentation. Can I get all of those drivers on? Which drivers are coming on? The demand is geospatial, so it also means where are the drivers? Are they in the right geospatial area? Do I need to move them all the way over across city? Are people in some neighborhoods are more price sensitive than others? You know, for example, maybe Kreuzberg versus Piberg in Berlin. People are willing to pay more in different neighborhoods. Then we have competition. They're also reacting. Maybe they've lowered the prices. Maybe they've increased the commission. There's traffic congestion, and then there could be events, right? So now you start to see how this is very complex, right? So just surge pricing originally was just get drivers on the road, but actually it's more complex than that. It's a whole system. Another thing we're doing, I mentioned that we also have an actual taxi service in Mexico City where we own Tesla cars and employ the drivers. One system optimization we do there is between rides, where do we place the cars? Right? It's not like ride hailing, organizing, self-organizing. We need to tell these drivers to go sit somewhere. So we need to understand where are the hotspots that they should wait for the next ride. And that's another system optimization, right? I don't look at one car. I look at all the cars and I look at all the demand to understand how to put them. So simulation was the second word I put in the title of the talk. And simulation is not something we hear about often. We're used to it in science and engineering, but not in data science. It's all about, you know, analytics, statistics, and then machine learning, and now neural nets. But if we think about this, what I just talked about were systems. So I'm thinking about the whole system, all the cars, the passengers, the ecosystem. And typically when we're doing data science, we're thinking about, oh, how do I personalize this ad? How much do I CRM? How much do I pay for this, you know, programmatic? Ranking within the app. It's a very individual experience. And we have models to do that, right? What I call here predicting at the atomic level. That's the low level. In our system, the drivers and the passengers. But if I try to now predict the whole system, I run into a bit of trouble because the system is too complex. And complex is different than complicated. Complex means that it is, in fact, unpredictable. So what do you do with a complex system? We're used to this in some physical systems, chemical systems, definitely in biological systems, and definitely in the most complex system we know on the planet, which is the human economy, right? So you have to simulate because you can't actually build models to predict it. And why is that? Because the passengers and our drivers, they're agents, they're intelligent agents, and they're interacting in a complex environment, right? So their attributes are changing as the system evolves. So I can't just write down an equation like we would in traditional physics and solve it like a differential equation, or I can't build a predictive model because you can't peg at any given point what you need to predict. So The only way you can do it, and this is in the most extreme cases, and urban mobility is one of those extreme cases, is the only way to see what a system does is to actually run it. That means to simulate it in some sense. Now, obviously, there's a massive cost. I just told you it's a very complex system. It's also a very complicated system. So if I just simulated all those variables and metrics, I would probably need a lot of features. I would need a lot of data, and I'd probably need an infinitely powerful computer. So you need to actually abstract and simplify. And as I've shown on the right then, so I take the complex behavior of a massive city like Mexico City, 30 million people, and I do abstract and simplify to what I think are essential, and hopefully I'm successful in that. And what kind of simulation models are we using? One is agent-based modeling. So, you agents are the cars, the drivers, and the passengers. There's the external influences and so on. And they're making decisions. They're deciding whether to accept a ride on both sides and so on. And that's what we call an agent, right? They have some agency and they make decisions. And you can put them on a grid. You can put them here in a hexagon tessellation. You can put them on actual road and so on. One thing we do have from what is part of AI is reinforcement learning, which is similar to agent-based model, is that there's feedback on these agents using concepts that are related to now in the whole world of reinforcement learning, neural networks and feedback loops and so on. So that's what we would do, and that's what we are doing. Now, if you're lucky, when you do a simulation, you might come up with some results that are understandable. Maybe you get some high-level insights, right? If I go back to this diagram on the right here, you have low-level predictability, but you have high-level insights, right? Comparing physics to biology. One's more low-level and one's more high-level, right?
Mr. Pillai, 1 minute, please.
Now, if you're lucky, you might get some insights, and you might be able to prediction on some new variables get the high level. But if it's a very complex system, like urban mobility, actually, you're typically going to be out of luck. And so we introduce a new concept of adaptation, right? So insights is what we do with basic analytics. Then we go to machine learning and AI, where we get prediction. And with insights, you can guide the system with some general understanding. With prediction, you can fully control the system. But if you don't have any understanding other than high-level insights and a simulation, then the best you can do in most cases is to adapt and self-organize. And what do I mean by adapt? For example, if there's a traffic jam, you can understand what kind of traffic jamming it is from your simulation, and then you can have some sort of heuristics to react. So you build up scenarios and you build up heuristics. And if you're really smart about it and you understand your system well from your simulation, you can build some local heuristics that self-organize, right? So similar how ants look for food, in a highly congested city, and it's actually done in Mexico City, you can control the traffic lights with simple heuristics. And that's what we want to do in urban mobility, in organizing our drivers, what kind of pricing and so on, is think of some good heuristics so that the system adapts, because we can't predict and control. Thank you. And if anyone is out there, of course, we're hiring. Everyone says that, but we are. Thank you very much.